cover on the face of the dune. What that is that's how vegetation shows up in our LiDAR data. And so this is a dune that has a lot of vegetation on it. And so when you have a highly vegetated dune, it has a root structure that actually gives more stability to that dune as well. So perhaps that dune can withstand a little bit more wave impact and would respond more slowly to waves impacting it. And so we're trying to sort of come up with this conceptual model of being able to, first of all, look at a dune and see these shapes and have some idea of the processes that are acting on that dune. And then from that, also be able to look at this and have some idea of how we might expect that dune to respond to a wave hitting it. And so your foredune form, or the shape of your dune, can be thought of as sort of an interaction between these sort of three main processes. You have your coastline dynamics, and that's things like, has the dune been eroded by waves? Is there adequate sediment supply? Has there been a lot of storms? So sort of your physical wave coastline dynamics that are acting on the storm. And then there are your aeolian processes, and that's how we naturally build up dunes. Wind moves the sand, deposits it in the dune, your dune grows. That's how dunes naturally recover. And then you have your management practices, and this is, in a natural system there is no management, but how much of our coastlines are actually natural, so we have to include this as an important part. And those are things like whether that's planting vegetation, putting in sand fences, beach nourishments, actual physically engineering structures of the dune. And so all these processes both interact with each other and then interact with the foredune form. And in fact, the shape of your dune can actually feed back and affect some of these processes themselves. And so the idea is if we can come up with ways to extract metrics out that describe the form that the dune is in, we might be able to come up with some sort of quantification of the different processes that have been acting on that dune. And so why is that important? Well, if you're trying to rebuild your dune after an event, you might want to know that this stretch of beach is recovering pretty well. We can see that there's an incipient foredune that's growing in our metrics, and so we know that aeolian processes are alive and well. We are trapping sediment, we are growing a dune. But if we don't see that incipient foredune formation along a certain stretch of coastline, that might be a clue to managers. Hey, focus on this stretch, put your sand fencing here, do your vegetation here, because this stretch of beach actually needs some help. So how are we going about trying to extract some of those metrics? And this work is still sort of in the early stage of its development. I don't have a list of these are the exact metrics you need and this is how we do it. We're still working on this. But if in this top panel here, this is a 50 centimeter DEM made from the terrestrial LiDAR data. Your blue colors are down on the lower beach. Your red colors are up on the dune crest. I don't know if you can see, you sometimes see sort of high frequency variations in that cyan color. I don't know if you guys can see those. Those are things like beach cusps. So we get really detailed morphology. And so the first thing I did was tried to calculate your cross-shore slope. And that highlighted this area of steeper slopes that's probably along your dune face. But it didn't really seem to be picking as many of the features out that I wanted to do. So the next thing I did was look at your surface curvature. And so what this is doing is it's treating it really as a surface instead of just a cross-shore transect. And so you go to each point and you look at a little box around that point and you calculate your curvature between that point and the points sort of diagonally and perpendicularly above and next to it. And curvature is basically the second derivative of the surface. And so that's finding places that you have changes in slopes. And so places that you have changes in slopes would really make those features like scarps and things like that stick out well. And so peaks in those curvature should be highly apparent. And so that's what your surface curvature looks like. And so we have a couple examples where If you look in these, there are sort of 3 regions along this stretch of beach where it seems like there's multiple peaks in curvature, in your surface curvature. And so if we look at some of those example profiles, the blue is sort of the standard elevation profile, and then the red is your surface curvature. And so one of the things to notice is that in all of these features, all of these dunes sort of have evidence of a recovering foredune in front of it, this sort of second hump where it's convexly shaped, sticking out. And so what you can do is if you find your dune toe, you might start to characterize recovering foredunes by 2 peaks in curvature between your dune toe and your dune crest. And so that's saying that, hey, these dunes are recovering. It's not always that easy. Sometimes it's really difficult to separate what we would call an upper beach berm and an incipient foredune. So if we look in this, so this is a zoom in of this section here, and you can see this yellow color here. That's not describing a dune feature, that's describing sort of this berm feature out here on the beach. And you can see it starts to get tricky when that berm feature sort of merges in with your incipient foredune. And so it's problem areas like this that we still have to figure out how to deal with in our metrics. But we're pretty excited about potentially being able to utilize this really detailed data on the face of the dune to get a better understanding of the processes that have been shaping that dune. Oh, and then this is sort of, this is on the flip side. So these are regions where we have more scarped dunes that are not recovering well. And you can see here's your dune toe, here's your dune crest, and there's no second peak in curvature between those 2 points. And so that characterizes some of these other regions of the beach. And then, it's important to remember that curvature doesn't tell the whole story. That's just describing some of the features that you see on the face of the dune. It's still really important to consider this overall elevation of your crest and your dune toe, in addition to things like the volume of the sediment. And then eventually the goal is to look at the longshore continuity of some of these features. So that's sort of how do we describe the state that the dune is in. That was the first piece of the dune question. And then the second piece was, okay, how do these different state dunes respond to a wave event? Please play. Okay, good, it's playing. So what we have here, and this is from that same nor'easter in March, and this is looking at the daily data that we extracted out of our terrestrial LiDAR. And this dune on the right here, this is an example of one of those bulldoze dunes, and I apologize, the scale of these 2 plots is not the same, which makes this a little bit confusing. But the D-low elevation for this dune, the elevation at the toe of the dune is 2.4 meters, and this was a little bit higher, that's 2.5 meters, but pretty similar in terms of what that D-low elevation was. And they had very different responses. Now these 2 dunes actually happen to be within about 20 meters of each other on the shoreline. So, and this was because this homeowner, post-Hurricane Sandy, had paid to have either a bulldozer come in and dump a bunch of sand in front of their house or had done beach scraping, whereas this homeowner had left their dune in the eroded state that it was. And so you can, if you look at the really rapid removal of this unconsolidated sediment, and this dune did erode some as well. It's not like it experienced no erosion, but the magnitude of erosion and the volume of the amount of sediment that was lost from this bulldoze dune was a lot higher than what was lost from this sort of more naturally stayed compact scarped dune. And we're still going through the quantification of a lot of this, and so hopefully we'll be able to come out with some metrics and sort of some prediction ideas associated with it. So this is my little graphic of putting it all together of why you need to care about what your beach and your dune and your surf zone looks like before the storm in order to get those predictions correct of what you can expect. So the idea is that you have your event parameters, and we can predict things like storm surge elevation and your offshore wave height and period. Those are model inputs that we already have ready to go. And so we could take those, and then if you know something about the morphology of your surf zone, maybe how many bars are in your surf zone that you might encounter. So you can say something about how much wave breaking would occur. And then you know something about what the slope of your beach is, because your beach slope can either it could enhance run-up if you have a steep beach, or if it's a flatter beach, you might get lower run-up. And then you need to know something about the morphology of your dune. And so if you know those 3 pieces of information, and you combine that with your event parameters, I think we could do a pretty good job at predicting what your storm impact is going to be. And so thinking about this is all well and good, but do we really have a way of getting that data before the storm? And that sort of led me to thinking, I got to this point in my research and I was like, hey, this stuff really matters. We either need to be able to predict it really well all the time, real time, and some people might argue that we're getting close to being able to do that. But so if we can't predict what the sandbars and the beach is going to look like all the time, can we come up with a way to rapidly measure it? And so this idea that if we can come up with a really quick way to measure your antecedent beach, dune, and surf zone morphology and have a quick data turnaround, could you feed that into these models to get accurate predictions? And so this led me to looking at the idea of using little unmanned aerial vehicles, UAVs, to see if we could try to come up with a way to collect that type of data from a UAV. And so what we're working on is being able to collect data on the elevation of your beach to get the dune and beach state, and then also the morphology of your surf zone from a really cheap, inexpensive, hand-launchable unmanned system. Now, I know there's a lot of issues with flying unmanned systems right now in the FAA, but I'm confident that the FAA will eventually come to their senses, and I want to have a methodology ready to go for when they do. And so what we've done is sort of taken a step back and said, okay, Claris is a great research tool to collect these data, but it's really expensive and it's not really good to give to everybody. So can we do this using really cheap cameras? So we got sort of 4 inexpensive $150 cameras, and we're using the cameras mounted on an aerial platform. And what we're doing is the cameras are looking at your beach and your surf zone as you fly along the coast, and we needed the multiple cameras because we needed to be able to see forward and see backwards so we could build up that time series of what the waves were doing. And so over here, we're using stereo photogrammetry to get the elevations of the beach, and then we're doing basically a flying Argus to get your sandbar morphology. And let's see, do I have, oh, I don't have, I thought I had one more slide in here. And so we're just started doing this, and we're really excited about the potential of this. And what we're finding is that you can do a lot with these inexpensive cameras, and you can get similar quality topography data to what we're getting with the LiDAR system, enough so that you could get accurate beach slope measurements and know elevations about the dune. And then we're getting the same type of data you can get with Argus. And so maybe you can use this map of your surf zone morphology to scale those offshore wave heights to account for how much wave breaking you might expect. And so if you could get this data collected a few days before the storm and be able to feed that into a model, then maybe you could do a better job at predicting your wave run-up and ultimately the overall response of the beach along the coastline. And so that's all I had for you. This is an example of the RGB point cloud that we get out of the UAV. So it's just like a LiDAR point cloud, but we also get the RGB color intensity associated with it. And it's really high resolution also. So I'm going to stop there. And do you guys have any questions?
So duck has been there for, I don't know, 50, 60 years. And at
30.
one point there were no development at all north or south of it. So what impact has the development over the history of duck, what impact does that have to the evolution of the beach run?
Well, one of the big things is that there was a lot of artificial sand fencing that was put in when they first started developing the coastline, and what that did was that really increased the elevation of the dunes along the front side of the beach. And so they built these really tall dunes, and some, traditional ideas of barrier island rollovers, you need to be able to overwash those dunes. And for a lot of the regions along here, those dunes are so high that it would take a really large event to overwash it. So on the plus side for development, the building of dunes was really good. On the flip side, you're not moving any sediment back and building up the dunes behind that front dune. And so what happens a lot, if you saw that pool was on the beach, is once like the first part of that high dune starts to go, then the rest of it is a lot lower, and so it can go faster. The other thing, which is really interesting up here in this development region, is that there was a setback distance that homeowners had to follow. They had to build their houses a certain distance back behind the dune. But what they were allowed to do is they were allowed to build pools within that setback distance. And so if you build a pool in your dune, when you do that, you are digging up all your dune sediment, all the volume of dune that's going to protect your house. You're removing it, you're digging a big hole, and you're putting a pool. And so if you noticed in that one of those first slides I showed you, during Hurricane Sandy, the waves were colliding. Sandy for us was a big event. It was not the biggest waves that we've ever seen at the FRF, but it persisted for about 3 or 4 days. So Sandy sort of moved very slowly up off the North Carolina coast. So we had waves colliding with the dune for multiple days. And so as the dune started to erode and reached these pools, there was a lot of scouring and everything that happened around these pools. And so it really exacerbated the dune response where folks had built pools in their dune. In terms of the longer term morphology, I don't look as much at that in my work, but I know where the pier is built actually happens to be extremely stable over the last 20 to 30 years. There's been a lot of erosion in a couple of hot spots along the coastline. This one up here is pretty interesting. There was an old inlet back in the late 1800s called Caffey's Inlet that was in that region. And that inlet closed, and what happened when the inlet closed, a lot of the sediment that was in the ebb tidal shoal sort of got spread along the beach and sort of moved on shore. And so there's actually a little bulge in the shoreline there. It sticks out. And we can, if you go back and look at sort of some of the historical area photographs, you can see that bulge sort of migrating down along the coastline. And where it is now is in that region where that erosional hotspot was that I showed you. And it's been really, in the last few storms, rapidly eating away at that bulge that sticks out. So that's some of the longer-term morphology in that area.
Another question? Well, this data, the models, they show mathematical equations. So what part of this data may be useful for the models?
So a lot of the models will predict what the morphology should look like at any given time. So you can compare what the morphological prediction is from the model to what the observations of the morphology is. But one of the things that, I don't know if Joe is still here, that Joe and I worked on was we actually fed the model what the morphology was and then let them to basically test to see if the hydrodynamics were correct in the model. So instead of letting the model try to evolve the morphology, we told it what it should be and then tested what the hydrodynamics were predicting, and then we're able to compare the really dense observations of wave data from the LiDAR with what the model was predicting.
So did you really retain the term dH by dt, the change of elevation over time, including the elevation of the land or sand or whatever?
So when we ran X-Beach, which was what Joe was running, we did not let it evolve the morphology. And so the first time we ran it, we did let it evolve the morphology. And it did such a terrible job that we said, okay, we're not going to let you try to predict the morphology. We're just going to tell you what it is and see if you get the waves even right to make sure that we were getting the hydrodynamic forcing right. Does that?
But you cannot get hydrodynamic correctly if you don't include the morphology term.
we were telling it what the morphology was.
You need to get the hydrodynamics right sometimes. So.
At one time step in the model, we gave it what the beach profile was and what the underwater bathymetry was, and said, propagate waves over that for that time step for an hour. And it wasn't even getting the hydrodynamic portion of that correct. When we let it evolve the morphology, it basically created a giant scarp in the beach, a giant vertical scarp in the beach. That was not, if you saw that nice smooth stepping back of the profile, that was not what we were getting in the model. Does that?
Maybe you guys can talk.
Yeah.
We'll do more, I think. Any other questions?
What's happening with the sedimentology of the beach during all of this?
So that's a good question. And so Heidi Wadman, who is also works at the FRF, is actually looking at that right now. Duck is sort of has a bimodal sediment distribution. So we have sort of a gravel, and then we also have a more traditional fine to medium beach sand. And so one of the questions is, when you expose a gravel patch, does that change some of the wave run-up? So do you get more percolation maybe when run-up goes over a gravel patch, and so then there's less, perhaps you get lower wave run-up, or there's more friction, so you might get lower wave run-up. And then how does sort of the interaction of those two different types of sediment, is it all the gravel that's going offshore and the fine stuff is staying onshore, or probably vice versa? And so looking at some of the sediment patterns, the heterogeneity.
Can I ask another
Yeah.
question? Could you explain to me in simplistic terms if the infragravity energy is affecting the gross three-dimensionality of the beach? I mean, you're seeing the beach is not straight, there are wiggles in it, okay?
Mm-hmm.
So is this just the offshore bar just affecting the waves coming in, or is there trapped energy between the bar and the beach?
All of the above would be my answer. So there are a couple of different sources of infragravity energy. You can have sort of infragravity energy that's related to your wave groups that are coming in from offshore. And there are oftentimes alongshore length scales associated with those wave groups. And so there are longshore length scales to those infragravity waves. And there's some interesting research at looking at sort of the alongshore length scales of those infragravity and how that affects what the shape of the bar is. And then as the waves break, they actually sort of release infragravity energy. And so you can sometimes get infragravity energy that gets trapped along the shoreline. And so there's a lot of different types.
Well, does that topography migrate, for instance, or does it just kind of go, does it move seaward, move landward, or does it actually move up and down the beach?
Both. Both, yeah. And that's why this is so hard. That's why predicting what your beach morphology is at any given time is so difficult, because there's cross-shore exchange of sediment,